So here is the Python version of how to do the Euler method. And I'm going to, okay, so if you don't want to do this using Python or anything similar to that, then go on to a different video. So for this, I'm going to try to keep things as simple as possible. So if you know how to use like IPython to play with things, or Jupyter Notebook to sort of have something more interactive for yourself, then that's great. But I'm just not going to show that. But definitely that's preferred if you know how to do that. And another thing is, probably we should use NumPy to do this, but if you know how to use NumPy, then go ahead and do that. And but also if you know how to use NumPy, you probably don't need to see this video. So I'm going to try to keep this simple and just use like pure Python stuff as much as I can. Okay, so I'm going to create a file. And you can use whatever text editor you want. So I'm just using some text editor here. And here is my setup, is this thing that I circled in blue. This is my differential equation to which I'm going to apply the Euler method. So this differential equation, x prime is 3x minus t, and x of 0 is 1/2 is my initial condition. So let me fill in some of those things. So I'll put r equals 3. That's what that's so I don't have to type 3 everywhere in case I want to change that at some point to some other choice. Then I'll just be able to change it up here at the beginning. And x0 equals 1/2. So let's just call that x0 equals 0.5. Okay, so the first thing I'm going to focus on is trying to generate a list of x values and t values. Then I'll look at plotting what I have. And remember, the goal is to hopefully end up with something that looks like this, but without actually using this. So no solving, no method of integrating factors. Sorry, I just realized my terminal window is really close to the edge of where it's recording, so I don't know if it's totally visible, but hopefully now you can see it. So to the extent that I can, I'm not going to use very fancy Python features. So I'm just going to basically generate a Python list that consists of all the t's and all the x's. And let's call these two lists t's and x's. So t's and x's. And let's start the list, each list with just one item. So t's starts with the initial t, which is t equals 0. So just 0. And x's starts with the initial x, which is 1/2, but I already defined that up here, so I can change it easily later on if I want to. So that's just x0. Okay, and as I go along, I'm going to like add items to these lists. So that'll happen in a loop. So I'm going to do a while loop, where in each iteration of the loop, I do some stuff, and let me stop the loop once I reach a certain time. So inside the loop, I'm going to be appending things to these lists. So I'll be adding something to the end of each list at each step of the loop. So if I want to know what is the last thing that I appended, then there's this convenient way in Python to just get the last position of a list. So t's -1 refers to the last value of t. So in a first iteration of the loop, the last value of t is also the first, since it's a list with one item in it, so it's 0. Okay, so I'm going to run this loop until the last value of t exceeds some end time. So in my Mathematica plot that I showed you earlier, I showed this plot running from time equals 0 to time equals 1 of my solution that I got using the method of integrating factors. So let me run things out to time equals 1 to start with. So as long as the last time that we filled in a row for is less than 1, we're going to do the following. So I'm going to hopefully in this portion of the code, I'll figure out the next x and t, and then once I figure them out, I'll append the new t to this list, and I'll append the new x to this list. Okay, so the new t, well, that's actually pretty easy. It's the old t plus delta t, right? Plus whatever is the time step. So that's one of these things that you have to sort of choose at the beginning, right? So I'm just going to choose, let's see, so I can't type the Greek letter delta here. Let me put it up here at the beginning with all these other parameters. So I'm going to use capital D, dt. How about that? Let me set it to be 0.01. Okay, so dt is 0.01. And I'm grouping all these things together because these are things that I want to tweak maybe every time I run the code and look at what happens. Okay, so the new t is going to be the old t, or the last t, plus dt. And then let's just fill in some placeholder code, something stupid. So this will be something stupid for now. Let's just make x always be 0, just so we can make sure our code is working, at least. So each time this loop runs, we append a new t value and we append a new x value. Let's let this run. Okay, so the first thing I might want to do is just run this and make sure there are no errors. So right now it's not going to print anything, but hopefully it also doesn't give an error. Okay, good, no errors. So at least the loop runs and it doesn't hang. It does not run infinitely. So it stops when this condition fails. So let's see, maybe I can print the t's and then print the x's. Maybe in between I'll print like some new lines to separate them, just so I can see what happens. Okay, that's not what I was expecting. Because I printed t and x, not t's and x's. So it printed the last value in the loop here. There we go. So it looks like the t's starts at 0, goes to 0.01, so that's t plus delta t. Then 0.02, that's t plus 2 delta t. 0, then delta t, then 2 delta t, then 3 delta t, and so on. All the way until we reach this one, and then we go over by a little bit. That's okay. Okay, and then the x's starts at our initial condition, and then it just does something stupid and sets it to 0 each time. So that's because we put in placeholder code. Let's now put in the actual code, not something stupid. So what should x be? Well, each time the new x should be the old x. So the old x is that. The last item in the running list of x's, plus the change in x, the approximated change in x. The approximated change in x is what I'm describing, kind of what I'm describing here. So I'm basically just doing this idea here. So the approximated change in x is the most recent information I have about the derivative of x times the time difference. And what do I know about the derivative of x? Well, for my differential equation, this is the only part where I put in the differential equation. So far in the code, all I've put in is like initial condition information. And I guess I put in a choice of r, but I haven't used it yet. So now finally I put in the differential equation. So what's the derivative of x? It's 3 times x minus t. So here I'm going to approximate that by saying 3 times the old x, the previous value of x, x's last item in the x's list, minus t. So by t I mean the last value that t took. Okay, so why not put in t here? Why am I putting in this? That's because t is the new value of t, right? And here I'm trying to evaluate the derivative. I'm trying to evaluate x prime, kind of like this. I'm trying to evaluate x. Really, let me look at this table. When I'm computing like what to put here, I'm using the previous derivative information, which relied on the previous row's t and the previous row's x. So here's the previous row's x and the previous row's t. All right, let's see how this works. Hopefully it'll run. Okay, let's see. So it starts here. Here's our list of t's. And then now our list of x's is looking more reasonable. Looks like it starts at 0.5 and then it starts increasing, which is some expected behavior. Now to plot this thing. So what should we do to plot this? I'm going to import matplotlib.pyplot as pult. So pult here is going to be a short name for all this that I don't want to write every time. And let me make sure I spelled all that right. So does it run with no errors? Yes. Now to make a plot, I think I can just do pult.plot. Let me remove these print statements. I don't want to just print out all that stuff anymore. I think I can do this. Put in the list of t's, put in the list of x's. Now really, this library that I'm using, matplotlib, is mainly designed for use with NumPy, which we're not using here. But if you know how to use NumPy, or if you want to learn, it's a good chance to learn. Look it up and use it. But right now what I'm doing with just pure Python is perfectly fine and sufficient for this simple project. Okay, so hopefully this creates a plot. Oops. Okay, I think it created a plot and then never showed it to me. Show. Aha. Okay, there we go. And that's what it looks like. And here's my old Mathematica plot running from time 0 to time 1. There's x on the vertical axis. And yeah, they look pretty similar. That's not bad. Good. Okay, so let me label the axes. That would be nice. So I just went and looked up the documentation for matplotlib to remind myself how to do that. So let's make the x-axis t, the y-axis labeled x. And let me also make this no longer be blue. Let me make it red so that I don't confuse it with my Mathematica plot information here. Let's use blue for the result of the theoretical analysis and red for the result of the numerical analysis. Okay, there we are. There it is in red, and now you see my axis labels. There's t and x. Now I want to compare them on the same plot. So yeah, they look similar when they're on different plots like this, but I want to see a more fine-grained comparison. Sorry. Okay. Let's see. So I think to do the comparison and get matplotlib to show the theoretical solution, so to show what I had in Mathematica here, I'm basically gonna have to somehow generate a list of x's that takes these exact values that I got using the method of integrating factors. So let's see. Let me create a new list. So I've got a list of t's and a list of x's. This is the list of x's that were determined numerically. So notice no method of integrating factors happened here. No differential equation solving happened here. All I put in is information from the differential equation. Now I'm going to create a new list of x's. So let's call x's theoretical. And that's going to be a list. So let's see, do I want to, how about I start it as a list of zeros? So here's a way of starting you know, if I type this, so let me show you in an interactive sort of thing. Let me use IPython. So if I type like a list of things like this, and then I multiply the list by a number, like 5 or something, then it gives me a list which repeats my list, like 323, that many times. So 323, 323, 323. Okay, there are way better ways to do this if you use NumPy, but I'm trying to show how to do it with just pure Python. So I'm going to make x theoretical start out as a list of zeros, and how many zeros do I want? Well, however many time values there are at which I want to have an associated x value. So however many time values there ended up being. So this will be a list of, so let me just show you the list. Yeah, so it's still generating the plot, but there's the list. It's a list of a bunch of zeros. That's x is theoretical right now. And it's as many zeros as there are time values to associate with. Now, to populate this list, how about I go, I do a for loop, and I go for each I for each possible index for the list of t's. So that means I is going to go 0, 1, 2, 3, etc. up until however many items are in this list minus 1. Then I'm going to say what I want x's theoretical at that position to be. So somehow it's going to be some function of t, where by t I mean the corresponding time at that index. So let's see. I will make it be what I got here in my solution that I got with the method of integrating factors. So 1/9 plus 1/3 t plus that. So 1/9 plus 1/3 times t, where by t I mean the time value at the same index in the list I, plus 1/2 minus 1/9 times the exponential. So if you're using NumPy, of course it's going to provide you with an exponential, but let me just use the one in math.exp 3 times t. Okay, and let's just print out x's theoretical to see that that's working. Okay, it's still generating the plot. No errors, good. And here's my printout of x's theoretical. That's pretty good, and it starts at 0.5, as should happen since I actually made the initial condition hold when I came up with that formula. Okay, looking good. Let's just add it into the plot now, so I don't want to print it out anymore. And let me try to get everything to show on the same screen here. So I think this works. Just listing. So here, what I'm telling it to plot is x's versus t's, right? The x's were determined numerically, and I'm having it plot against the t's. So in the plot, it's using this for the x-axis, the horizontal axis, and this for the y-axis, the vertical axis, and it's plotting corresponding points. So it's looking at these are both lists, so it's looking at index 0 first, and it's looking at the 0th position of this list, 0th position of this list, and that's giving it a coordinate in that 2D space. And then it looks at index number 1, so the 1 position of this and the 1 position of this. That's giving it another coordinate, and then it draws a line segment connecting them. And then it keeps going down the list, drawing line segments, and that's the curve that you get. And then this is just me saying I want it to be in red. So now I'm going to take the same t's, and then I'm going to create another plot, if this works the way I remember, and I'll make it be in blue. Blue to match the blue curve you saw in Mathematica for the analytical solution. Okay, so let's see. There it is. Okay, so the red one is our numerical solution, and the blue one is the theoretical exact solution. So the blue one is the one we got using the method of integrating factors. The red one we got without any differential equation solving, just by taking Euler steps, using the Euler method. They're pretty darn close, right? But they're not perfect. So you see they start out close, they start out kind of perfect. Here, I mean, for a while, the lines are basically on top of each other. You can't even see that there's two lines. But they diverge more and more the more you run time along. So yeah, you're seeing that the error accumulates as time runs along. If we let time run for longer, so let's try that. Let's let time run for longer. So right now time is running out to 1 unit of time. Let's let it run out to 2 units of time. Then it looks like this. Yeah, so it looks like the gap size is the same as before, but the y-axis, or the x vertical axis scale is now way different. It used to run from 0 up to like 8 or something. Now it's 0 up to like 160. So the same, visually the same size gap is actually a much larger error. So this is a very large error here compared to before. So the error, how far we are off at 2 units of time, is much more than how far we were off at 1 unit of time. Here's 1 unit. You can barely see it with these axes scaled like this. Another principle we can observe is what happens when we change the time step. So let me change this back to 1. Really, this should be a variable that I can control up here, so I don't have to mess with the internals of the code. So let's just make the end time be 1. And let's make the time step be 0.1 rather than 0.01, and look at what happens. Okay, now the error is much worse than the original plot we saw running out to 1, right? The red is really severely underestimating what's really happening, which is the blue. We can make it even worse for fun. How about 0.2? So this is a time step of 0.2 with a time running from 0 to 1. So it's basically like 5 or so times. You know, you can even see the blocky line segments, right? So now it's even worse. One thing I realized about this code is that it deceptively looks like it allows me to change what R is. Oh, well, okay. It doesn't allow me to. Okay, so I set R up here, but then for some reason I just typed 3 here, where my initial idea was I can put in R and then modify it from up here. But even if I had done that correctly, that still wouldn't have been correct, because I used the specific R value of 3 to determine what C makes my initial condition work, right? So changing this R is going to mess with my initial condition and make this no longer be the correct way to satisfy this initial condition. So this code has failed to allow me to change R. I should leave it like this. But you can imagine how you would have written something a little bit more general. Here in your analysis you would have left this as R rather than putting 3, and then here when you get what your C is, it'll be something involving R's, right, rather than being a number like this. Then here in your theoretical solution, when you put in what C is, it'll be that expression involving R's. R is set up here at the beginning, and R would show up here. Okay, not too important anyway. So there it is. There's the my as simplistic as possible that I could come up with Python way of doing the Euler method for this contrived differential equation.